So, what is channel coding and why do we need it? When a signal is sent over long distances, the signal experiences noise during transmission, which may introduce errors in the message as it is being received. Channel coding provides a framework for forward correction, so that we can detect and fix errors during the reception of the message. This is done by adding extra bits, which can allow for the error detection and correction. So while there is extra overhead, uh, channel coding aims to reduce the need for retransmission of messages to improve the overall throughput of the system.
The BHC codes are a type of block code where data is divided into fixed size blocks before encoding, which is pretty useful for correcting multiple random errors within the data stream. They're designed to be efficient with a lower cost to compute when encoding, and they're pretty ideal for systems that are going to have like limited processing power. BHC codes probably perform the best in environments where errors are infrequent and predictable, such as wireless communication systems and audio media with lower to moderate noise levels. Turbo codes combine two or more convolutional codes using an interleaver. These concatenations create redundancy in the data stream that's transmitted, which helps improve the error correction capabilities. Since there's an iterative decoding within turbo codes, the receiver performs multiple passing over of the data to refine the error estimates, which makes it pretty complex. The trade-off is a significant improvement in error correction, but requires way more computations to be made. Turbo codes also really shine in high noise environments due to that reason, like mobile and satellite communications. This is due to their ability to achieve like a near optimal error correction rate, and they're a great choice in where severe air conditions are common.
Our simulation, we started by generating a random message with the Bernoulli binary block in Simulink from MATLAB or MathWorks. We use two encoding methods, and you can see that with the BCH encoder and turbo encoder, as well as in the third one at the bottom, we don't use any encoding. Um, you'll notice that we use QPSK modulation. The modulation isn't really relevant to our actual results, but it does have a nice little feature that will make decisions to uh, bring the message back to between 0 and 1, which can help because the noise can bring it to levels above 0 and 1. And for the BCH decoders and turbo decoder to work properly, the message should be between 0 and 1. Um, the AWGN channel generates white noise. We set that to use SNR, so we could modify SNR because that is our control variable for our simulation and research. Then we also, for the turbo encoder, we use a trellis of 13, 15, 1, 3, 1, 5, 1, 7. These are octal. And we use a message of length 20. For the BCH encoder, we use a code word length of 20 as well as a message length of 5. Then the decoders decode the message. It's basically all the exact same, but you will notice that before the turbo encoder, there's a unipolar to bipolar converter. The unipolar to bipolar converter converts the unipolar message to a bipolar one, which is needed for using the turbo decoder. And then that all feeds into different error rate calculations, which, as you might expect, calculate the error rate.
So let's talk results. As Josh said, the main independent variable we were changing was SNR, and the main dependent variable we were measuring in our simulations was BER, bit error rate. So looking at the graph, you can see right away, and at the table, kind of at both extreme ends of the SNR values we tested, the control group and the two coding methods actually performed nearly identical. So at like really high SNR values, like above 10, above 20, near 20, the bit error rate kind of approaches 0 for all three groups, or it hits 0. And at really low SNR values, the bit error rate approached 0.5. However, in the middle, like between -10 to 10 decibels, the coding methods, BCH and turbo coding, both outperformed the control by a pretty significant margin, especially the turbo code. For any given SNR in the range of -10 to 10 decibels, the bit error rate of the encoded systems is lower than the uncoded system. We never directly measure coding gain in any of the trials, but we were able to calculate it after the results were collected. So we did use it to help interpret our results. So if you don't know what coding gain is basically like a measure of signal quality improvement from uncoded channel to coded channel. So just to give you an example, if at the same bit error rate of 0.2, if one channel has a SNR value of 2 decibels and the other has an SNR value of 4 decibels, you might see a 2 decibel improvement in SNR at a given bit error rate. So that's coding gain, 2 decibel gain. So coding gain begins to increase drastically at bit error rate levels below 0.3. And you can just see this visually looking at the graph. Above 0.3, they're very close to each other, but below 0.3, they really start to spread out from each other. And the gain reaches its maximum at 0 bit error rate with coding gains of 5.59 decibels and 8.85 decibels for the BCH and turbo coding methods, respectively, over the control. So what that essentially means is you can have an SNR that is 8.85 decibels weaker with turbo coding than with no coding in order to reach the same BER of 0.
In terms of our discussion, for expectations versus our simulation results, we had expected that BCH would be better with less white noise due to the coding method being better with sustained random errors compared to turbo coding, which is better with bursty errors. This expectation lined up with the majority of our results that we found through simulation. Just a note, our simulation is not representative of all circumstances. Modifying parameters such as the trellis of the turbo encoder or the message lengths and code word lengths of the BCH can impact results. For our coding gain analysis, the coding gain generally increased as the bit error rate approached 0. And the difference in coding gain between BCH and turbo coding increased as bit error rate approaches 0. Turbo coding only needed a minimum of 2.5 of a signal to noise ratio to get a bit error rate of 0, whereas BCH coding needed a minimum SNR of 10 to get a BER of 0. This demonstrates that turbo coding performs better than BCH coding in our experiments in terms of bit error rate and coding gain.
Some anomalies. One anomaly that we found was, as you can see in the graph above, the bit error rates they level out towards around as they approach around 0.5. This makes sense as we approach higher and higher SNRs, the data becomes more and more random. If it was completely random, we'd expect a bit error rate of 0.5 because half of the bits would be wrong and half of them would be right. One thing that's interesting, that one side effect that we see that because of this is we see that at certain points the control, we have negative coding gains as the control actually has a better bit error rate at the same SNR as BCH and turbo at these higher levels, simply because the data is becoming more and more random. It also shows that the BCH and turbo coding algorithms don't do well in either case once you surpass a certain volume of errors